Saturn, the sixth planet from the Sun, stands as a beacon of wonder and scientific intrigue in our solar system. Its magnificent rings, first observed by Galileo Galilei in 1610, have made it one of the most iconic celestial objects. Saturn's allure is not merely in its aesthetics, but in the wealth of scientific questions it poses about planetary formation, the behavior of gases, and the potential for life in its system of moons. As one of the gas giants, Saturn's study reveals much about the forces that shaped the early solar system and continues to shape our understanding of the cosmos. The rings of Saturn are among the most extraordinary features in the solar system. Made up of countless particles of ice and rock, they orbit the planet in a delicate balance of gravitational forces. Though they stretch hundreds of thousands of kilometers in diameter, the rings are remarkably thin, often no more than 10 meters thick. These particles range in size from microscopic dust grains to boulders the size of houses, constantly colliding and breaking apart in a cosmic ballet. The precise origin of Saturn's rings remains a topic of debate. Some scientists propose that they are the remnants of a moon that was torn apart by Saturn's gravity, while others suggest they may have coalesced from debris left over from the formation of the solar system. The rings are divided into several regions, with the most prominent being the A, B, and C rings. These are separated by gaps such as the Cassini division, a dark band discovered in the 17th century that adds to the visual complexity of the rings. The Cassini spacecraft, which orbited Saturn from 2004 to 2017, revealed much about these rings, including their dynamic nature. Far from being static, the rings are constantly shaped by gravitational interactions with Saturn's moons, known as shepherd moons, and even by Saturn's magnetic field and atmospheric forces. The rings act as a laboratory for studying the physics of orbital mechanics and planetary formation. Saturn itself is a giant ball of gas, primarily composed of hydrogen and helium. Beneath its gaseous exterior lies a core of rock and ice, surrounded by layers of metallic hydrogen created under immense pressure. Saturn's atmosphere, though less turbulent than Jupiter's, still hosts extreme winds and storms. Winds in the upper atmosphere can reach speeds of 1,800 kilometers per hour, faster than the strongest hurricanes on Earth. These powerful jet streams drive the formation of bands and vortices in Saturn's atmosphere, giving the planet its characteristic yellowish hue. The coloration is due to the presence of ammonia crystals and other compounds in the upper layers of the atmosphere, which scatter sunlight. One of Saturn's most unusual atmospheric features is the hexagonal storm located at its north pole. First observed by the Voyager spacecraft, this enormous, six-sided pattern is a jet stream of high-speed winds encircling the pole. Measuring about 30,000 kilometers across, the hexagon's origin remains mysterious. Some scientists believe it is caused by differences in wind speeds at varying altitudes, while others speculate that it may be related to deeper atmospheric dynamics within the planet. Saturn's moons provide an equally fascinating area of study. Titan, the largest, is one of the most Earth-like bodies in the solar system. With a dense nitrogen-rich atmosphere and lakes of liquid methane and ethane, Titan's surface is shaped by similar processes to those that occur on Earth, such as rainfall and erosion. The presence of organic molecules in its atmosphere has made Titan a key focus in the search for the chemical precursors to life. The Huygens probe, which landed on Titan in 2005, revealed a landscape shaped by methane rain and rivers, a place where conditions might mimic those on early Earth. Enceladus, a smaller moon of Saturn, has captured scientists' attention for different reasons. Beneath its icy crust lies a vast ocean of liquid water, kept warm by tidal forces exerted by Saturn's gravity. In 2005, the Cassini spacecraft discovered plumes of water vapor erupting from cracks in Enceladus's surface, and subsequent analysis revealed that these plumes contain organic compounds. This discovery has made Enceladus one of the most promising places in the search for extraterrestrial life. The presence of water, heat, and organic molecules suggests that this small moon could harbor microbial life in its subsurface ocean. Saturn's system offers profound insights into the processes that shape planetary systems and their potential for harboring life. The Cassini mission, with its 13 years of observations, revolutionized our understanding of the planet, its rings, and its moons. It revealed that Saturn is not just a gas giant with rings, but a dynamic system full of scientific surprises, from the complex interactions of its moons and rings to the mysteries of its atmosphere and magnetic field. As we continue to explore the outer solar system, Saturn remains a key destination for future missions. It invites us to delve deeper into the questions of planetary formation, the possibility of life beyond Earth, and the mechanisms that govern the behavior of gas giants. The study of Saturn is not just about understanding a distant planet. It is about expanding our knowledge of the universe and our place within it. The majestic rings, the alien landscapes of Titan and Enceladus, and the vastness of Saturn's atmosphere remind us of the grandeur and complexity of the cosmos, urging us to keep exploring the frontiers of space science. Beyond the stunning beauty and scientific mysteries of Saturn, the planet's immense size and composition offer key insights into the broader mechanics of the solar system. Saturn is the second largest planet, dwarfed only by Jupiter, and its gravitational influence plays a significant role in shaping the paths of objects that orbit the Sun. Understanding the intricacies of gas giants like Saturn is crucial to grasping the formation of planetary systems, both within our solar system and in exoplanetary systems across the galaxy. Saturn's composition provides a window into the conditions present in the early solar system. Like Jupiter, it is composed primarily of hydrogen and helium, elements that were abundant in the solar nebula from which the planets formed. However, unlike the smaller rocky planets such as Earth and Mars, Saturn did not form through the accretion of heavy elements. Instead, its mass allowed it to capture a vast envelope of gas, locking in clues about the early stages of solar system evolution. Studying Saturn's atmosphere, where pressure and temperature increased dramatically with depth, helps scientists understand how these processes might unfold on other gas giants orbiting distant stars. The evolution of gas giants is intricately linked to the dynamics of their moons. Saturn's complex system of more than 80 moons offers a laboratory for studying interactions between planetary bodies. Titan, Enceladus, and several other moons are not merely satellites, they are dynamic worlds that interact gravitationally with the planet and each other. These interactions can result in tidal forces that cause internal heating, as seen on Enceladus, where tidal friction helps keep its subsurface ocean liquid despite its great distance from the Sun. The ongoing exploration of Titan, Saturn's largest moon, reveals a unique window into the potential for life on other worlds. Titan's thick atmosphere and stable liquid bodies on its surface, a rare combination in the solar system, suggests that it might have conditions that, while drastically different from Earth, could support life. The discovery of complex organic molecules in Titan's atmosphere by the Cassini mission supports this idea. These molecules, which are the building blocks of life as we know it, hint at the potential for prebiotic chemistry, a key step toward the development of life. Future missions to Titan, including the upcoming Dragonfly mission, aim to explore this world in greater detail, searching for signs of biological processes and deeper understanding of its chemistry. Enceladus, with its geysers of water vapor, continues to surprise and excite scientists. Its subsurface ocean, hidden beneath kilometers of ice, is kept warm by internal heating mechanisms driven by Saturn's gravity. Cassini's flybys through the plumes erupting from Enceladus allowed scientists to sample the water vapor and analyze its composition, finding a mixture of organic compounds, salts, and even molecular hydrogen. This suggests that hydrothermal vents, similar to those found on Earth's ocean floors, could exist on Enceladus, providing an energy source for life. The presence of these compounds makes Enceladus a prime target for astrobiology, and future missions may one day land on its surface or even send probes to explore its ocean directly. Saturn's influence extends beyond its rings and moons. Its gravity affects the orbits of comets and asteroids in the outer solar system, helping to shape the region known as the Kuiper Belt, which lies beyond Neptune. Saturn's position and mass have also contributed to the stability of the solar system, acting as a barrier that deflects many potentially hazardous objects away from the inner planets, including Earth. This protective role, combined with its role as a host to fascinating moons, solidifies Saturn's importance in our broader understanding of how solar systems evolve and sustain life. The Cassini mission, which orbited Saturn from 2004 to 2017, marked a golden age of exploration for this gas giant and its moons. Named after the Italian-French astronomer Giovanni Domenico Cassini, who discovered several of Saturn's moons in the 17th century, the mission provided unprecedented insight into the planet's complex system. Cassini revealed that Saturn's rings are far younger than previously thought, possibly only a few 100 million years old. It also confirmed that Saturn's moons are more geologically active than expected, with water ice geysers on Enceladus and lakes of methane on Titan. One of the most dramatic moments of the Cassini mission was its final descent, known as the grand finale, where the spacecraft deliberately plunged into Saturn's atmosphere, transmitting data until the very last moment. This ensured that no contamination would ever occur on Saturn's moons, preserving their pristine environments for future study. Cassini's data continue to provide insights, as scientists analyze its findings to piece together the history and future of this giant world and its moons. The study of Saturn is not limited to understanding a single planet. It is a gateway to broader questions about the formation of planetary systems, the nature of gas giants, and the potential for life beyond Earth. Saturn challenges us to think big, to explore the possibilities of life in environments vastly different from our own, to understand the forces that shaped our solar system, and to dream of what discoveries await in the outer reaches of space. As we send new missions to explore this distant world, Saturn will continue to captivate our imagination and expand the frontiers of our knowledge. The legacy of exploration left by the Cassini mission is only the beginning, as Saturn beckons future generations of scientists and explorers to unlock the mysteries it holds. Saturn, with its immense scale and complexity, stands as a reminder of how much remains to be discovered in our cosmic neighborhood. The planet and its moons reveal a wealth of information about the processes that shape not only our solar system but potentially others as well. Each aspect of Saturn's system, from its turbulent atmosphere to its iconic rings and geologically active moons, offers a unique opportunity to deepen our understanding of planetary science, astrobiology, and the potential for life in environments that are vastly different from Earth. One of the most captivating aspects of Saturn's system is the sheer diversity of its moons. While Titan and Enceladus have taken the spotlight due to their potential for hosting life, the dozens of smaller moons orbiting Saturn each tell their own story. Some of these moons, like Mimas, resemble small, frozen worlds with impact craters marking their surfaces. Mimas is sometimes called the Death Star moon due to the enormous crater on its surface, which gives it an uncanny resemblance to the fictional space station from Star Wars. Others, like Iapetus, present strange and unexplained features, such as a dark hemisphere that contrasts sharply with its bright opposite side. Scientists are still working to understand what could have caused such stark dichotomy in surface color. Then there is Hyperion, a moon with a highly irregular shape and a chaotic rotation, tumbling unpredictably as it orbits Saturn. Hyperion's surface is covered in deep craters, which gives it a sponge-like appearance. Its rotation is so erratic that it was one of the first moons to challenge our understanding of how celestial bodies behave. These smaller moons may not have the geological activity of Titan or Enceladus, but they provide important clues about the history of Saturn's system and the broader processes at play in the solar system. In addition to its moons, Saturn's magnetic field is a key area of scientific interest. Like Jupiter, Saturn has a powerful magnetic field that extends far into space, creating a magnetosphere that influences the behavior of charged particles in its vicinity. Saturn's magnetosphere is enormous, stretching millions of kilometers into space, and plays a critical role in shaping the environment around the planet. This magnetic field is generated by the motion of metallic hydrogen deep within Saturn's interior, where the pressures are so high that hydrogen behaves like a liquid metal. The study of Saturn's magnetosphere not only helps scientists understand the dynamics of gas giants, but also offers insights into the behavior of magnetic fields in other planetary systems. The interaction between Saturn's magnetosphere and its moons is particularly fascinating. For instance, the geysers on Enceladus eject material into space, some of which becomes trapped in Saturn's magnetosphere, forming a tenuous ring of particles around the planet. These particles interact with the magnetic field, creating auroras at Saturn's poles. Brilliant light shows similar to the northern and southern lights on Earth, but on a far grander scale. These auroras are influenced by the planet's rotation and the solar wind, making them a dynamic and ever-changing phenomenon. Saturn's ring system, too, is affected by the planet's magnetosphere. The interactions between the particles in the rings and Saturn's magnetic field create complex patterns of movement and structure within the rings. Scientists are still unraveling the ways in which these interactions shape the appearance and behavior of the rings, but it is clear that Saturn's magnetic field plays a central role in the dynamics of its entire system. Looking ahead, the future exploration of Saturn holds immense promise. NASA's Dragonfly mission, set to launch in the mid-2020s, will explore Titan in greater detail than ever before. This groundbreaking mission will send a rotorcraft to fly over Titan's surface, allowing scientists to study the Moon's complex atmosphere, surface chemistry, and potential for life in unprecedented detail. Dragonfly will search for the building blocks of life and examine Titan's surface up close, potentially uncovering evidence of prebiotic chemistry or even primitive life forms. At the same time, new missions are being considered to return to Enceladus and further investigate its subsurface ocean. The discovery of water ice plumes containing organic compounds has made Enceladus a focal point for astrobiology, and scientists are eager to send landers or probes to collect samples directly from its ocean or ice surface. These missions would be designed to answer one of the most profound questions in science. Could life exist beyond Earth, and if so, what form might it take? Saturn's exploration also raises important philosophical and ethical questions. As we venture deeper into the outer solar system, we must consider the implications of contaminating these pristine environments. The Cassini mission ended with a controlled descent into Saturn's atmosphere to avoid the possibility of contaminating Titan or Enceladus with Earth-based microbes. Future missions will need to be equally careful, particularly if they involve landing on moons with potential habitability. The search for life in the solar system is not just a scientific endeavor, it is also a responsibility to preserve the integrity of the worlds we explore. As we continue to unlock the secrets of Saturn and its moons, we are reminded of the vastness and diversity of the solar system. Saturn's system is a microcosm of the broader universe, offering insights into the forces that shape planets, moons, and rings, and the conditions that might give rise to life. Each discovery adds a new layer to our understanding, deepening our sense of wonder about the cosmos and our place within it. Saturn invites us to keep looking outward, to push the boundaries of human exploration, and to dream of what might lie beyond the horizon. It is a reminder that, as much as we have learned about the solar system, there is still so much more to discover. The study of Saturn is a testament to human curiosity and the unquenchable desire to understand the universe, a journey that will continue to inspire and challenge us for generations to come. Saturn, with all its grandeur and mystery, remains a symbol of humanity's desire to understand the cosmos. Each new discovery about the planet and its moons offers not just scientific insights, but also philosophical reflections on the nature of our universe and our role within it. The exploration of Saturn and its system pushes the boundaries of what we know and invites us to ask deeper questions about the origins of life, the mechanics of planetary formation, and the potential for life beyond Earth. One of the most profound aspects of studying Saturn is the opportunity to better understand planetary systems both within and outside our solar system. Gas giants like Saturn serve as natural laboratories for scientists to explore the processes that govern planetary behavior. While we know that gas giants are common in the universe, with thousands of exoplanets discovered orbiting distant stars, Saturn provides a close-up example of how these massive planets interact with their moons, rings, and magnetic fields. This information can be applied to other planetary systems, helping us unravel the mysteries of exoplanets, particularly those that orbit stars very different from our Sun. Saturn's complex system of moons continues to fascinate scientists, not just because of the possibility of life on moons like Titan and Enceladus, but also because they offer insights into planetary evolution. The gravitational interactions between Saturn and its moons create dynamic environments that reveal the ongoing processes of planetary change. For example, Enceladus, with its subsurface ocean and erupting geysers, is a reminder that even small, distant moons can harbor extraordinary geological activity. This opens the door to the possibility that moons orbiting gas giants in other star systems could also have active environments and the potential for life. Titan, with its thick atmosphere and liquid methane lakes, serves as a key to understanding how planetary environments can differ dramatically from Earth's while still offering conditions that may support life. Titan's atmosphere is dense enough to protect the surface from cosmic radiation and its methane cycle, where liquid methane rains down from the atmosphere forming rivers and lakes, parallels Earth's water cycle. This raises fascinating questions about the variety of conditions that might give rise to life. Titan's surface is a cold, alien landscape, yet its chemistry could provide valuable clues to the processes that led to the development of life on Earth, or perhaps life that could evolve under vastly different conditions. The study of Saturn's atmosphere also offers essential clues to understanding the behavior of gas giants. Unlike rocky planets, gas giants do not have a solid surface, and their outer layers consist of thick clouds of gas, primarily hydrogen and helium. These gases form layers under immense pressure as one moves deeper into the planet. Saturn's atmosphere is less turbulent than Jupiter's, but is still home to powerful storms, including the planet's hexagonal jet stream at the North Pole, a feature that remains a mystery to scientists. This storm, with its six-sided shape, challenges conventional understanding of atmospheric dynamics, and studying it could lead to breakthroughs in understanding how planetary atmospheres work, not just on Saturn, but on other gas giants both in our solar system and beyond. Another captivating aspect of Saturn's system is the interaction between its rings and moons. Saturn's rings are not static. They are constantly changing due to gravitational interactions with the planet's moons and external forces. These interactions cause waves and ripples in the rings, which can be observed and studied to learn more about the forces shaping them. The rings are also affected by Saturn's magnetic field, which traps charged particles and influences the movement of particles within the rings. This dynamic relationship between the rings, moons, and magnetosphere demonstrates the complex interplay of forces in a planetary system, offering a model for understanding other ringed planets, including exoplanets discovered with ring systems. The legacy of the Cassini mission looms large over our understanding of Saturn. Cassini's detailed observations transformed our view of the planet, revealing the intricacies of its rings, the activity of its moons, and the mysteries of its atmosphere. The mission provided data that will be analyzed for decades, helping scientists piece together the history of Saturn and its place in the solar system. Cassini's grand finale, where the spacecraft dove into Saturn's atmosphere, was both a dramatic end and a new beginning, an opportunity to gather direct data from the planet's atmosphere, while ensuring that Saturn's moons, particularly those with the potential for life, remain uncontaminated by Earth-based organisms. Future missions to Saturn are already in the works. NASA's Dragonfly mission, scheduled to explore Titan, promises to build on Cassini's legacy by examining the moon's surface and atmosphere in even greater detail. Equipped with a drone-like rotorcraft, Dragonfly will fly over Titan's surface, landing at multiple locations to conduct experiments and gather data. This mission will not only enhance our understanding of Titan's chemistry and the potential for life, but also offer lessons for future exploration of other moons in the solar system and beyond. Beyond the scientific endeavors, Saturn's exploration sparks deep philosophical reflections about our place in the universe. As we peer deeper into the mysteries of Saturn and its moons, we are reminded of the interconnectedness of all things in the cosmos. Saturn, a distant giant shrouded in clouds, holds the potential to answer some of the most profound questions about the origins of life, the nature of planetary systems, and the forces that shape our universe. The search for life on moons like Enceladus and Titan challenges our assumptions about what is required for life to thrive. Could life exist in a cold, methane-rich environment like Titan? Could microbial life flourish in the dark, pressurized ocean beneath Enceladus's icy crust? These questions force us to broaden our understanding of habitability and reconsider the limits of life as we know it. Saturn, in this sense, is not just a destination for exploration, it is a gateway to deeper philosophical inquiries about the nature of life and the possibilities that await us in the vast expanse of space. As we continue to explore Saturn, we are reminded of the power of curiosity and the endless potential of human discovery. Saturn invites us to look beyond our own world and consider the vastness of the cosmos, where even the most distant and mysterious planets can offer clues about our origins, our future, and the universal forces that connect us all. It stands as a testament to the beauty and complexity of the universe, challenging us to continue our exploration and to seek answers to the questions that have captivated humanity for millennia. The journey to Saturn and beyond is far from over, and each new mission brings us closer to understanding the true nature of the cosmos and our place within it. The exploration of Saturn serves as a powerful metaphor for humanity's unyielding quest for knowledge, symbolizing both the progress we've made and the vast mysteries that still lie ahead. Each mission to Saturn has revealed not only the planet's grandeur, but also the complexity and beauty of our entire solar system. Saturn's rings, moons, and magnetic field provide a diverse and dynamic laboratory where the fundamental forces that shaped our solar system continue to unfold, offering invaluable lessons for the study of distant worlds and exoplanets. As we look forward to future missions, it is clear that Saturn remains a focal point of scientific discovery. The study of this gas giant offers insights not only into planetary science but also into broader cosmic phenomena. For instance, Saturn's magnetic field interacts with the solar wind in ways that teach us about the nature of space weather, how the sun's energy impacts planetary atmospheres and environments. The lessons learned from Saturn's magnetosphere, its interaction with the solar wind, and its auroras can be applied to the study of other star systems and help scientists better understand the dynamics of exoplanetary atmospheres. Saturn's influence extends beyond the planet itself to its moons, which continue to fascinate scientists. The ongoing study of Titan, Saturn's largest moon, is particularly significant. Titan is the only moon in the solar system with a dense atmosphere, and its methane lakes and rivers create a surface environment that is in many ways a mirror image of Earth's own hydrological cycle. But unlike Earth's water-based system, Titan's cycle is driven by methane and ethane, which exist as liquids at the moon's frigid surface temperatures. The upcoming Dragonfly mission, which will send a rotorcraft to explore Titan's surface, is a critical step in the search for the conditions that might foster life beyond Earth. Titan, with its stable lakes, rivers, and atmosphere rich in organic molecules, is one of the most Earth-like environments known to us, albeit at extremely low temperatures. If life could emerge in such an environment, it would fundamentally alter our understanding of biology and the conditions under which life can exist. Dragonfly will explore Titan's dunes, lakes, and potential sites of prebiotic chemistry, taking samples and analyzing the moon's surface in unprecedented detail. This mission represents not just an exploration of a distant world, but a broader search for life's building blocks in the universe. If Titan harbors the ingredients for life, it may offer clues to the processes that led to the emergence of life on Earth. Moreover, the discovery of life, or even just the precursors of life on Titan, would have profound implications for the search for extraterrestrial life elsewhere in the galaxy. Enceladus, too, remains a high-priority target in the search for life. Its subsurface ocean, discovered by the Cassini mission, continues to inspire speculation about the possibility of microbial life thriving in the dark, icy depths. The geysers that erupt from cracks in Enceladus's surface provide a direct connection between this hidden ocean and space, allowing future missions to sample the water without needing to drill through miles of ice. The discovery of organic compounds in these plumes suggests that Enceladus may possess the essential ingredients for life, including water, energy, and complex chemistry. The prospect of finding life, or evidence of prebiotic processes, on moons like Titan and Enceladus highlights one of the most profound questions facing humanity. Are we alone in the universe? The study of Saturn and its moons directly addresses this question, providing a framework for understanding how life might emerge in environments vastly different from Earth. The discovery of life on another world, even if it is microbial or rudimentary, would fundamentally alter our perspective on our place in the cosmos. It would suggest that life is not unique to Earth, but rather a natural consequence of the physical and chemical processes that unfold in a variety of planetary environments. Beyond the scientific implication, such a discovery would raise profound philosophical questions about the nature of life, intelligence, and consciousness. If life can emerge in the cold methane lakes of Titan or the icy oceans of Enceladus, what does that say about the potential for life in the vast unexplored regions of our galaxy? Could there be intelligent civilizations out there, developing under conditions that we can barely comprehend? The study of Saturn is not just about understanding our own solar system. It is about exploring the possibilities for life throughout the universe. Saturn's moons, its rings, and its storms are all part of a larger story, one that stretches beyond the bounds of our solar system and into the realms of cosmology and astrobiology. Saturn's role as a gas giant, with its complex gravitational and magnetic interactions, provides a microcosm of the processes that shape the formation and evolution of planetary systems throughout the galaxy. By studying Saturn, we gain insights into the broader processes that govern the universe, from the formation of planets and moons to the conditions that might allow life to emerge. The exploration of Saturn also reminds us of the limitations of our current technology and knowledge. While missions like Cassini have provided unprecedented detail about the planet, there is still much we do not understand. The precise origins of Saturn's rings, for example, remain a mystery. Some scientists believe the rings are relatively young, formed from a shattered moon or comet, while others argue that they may be much older, perhaps dating back to the early days of the solar system. The ongoing study of Saturn's rings, their composition, and their dynamic interactions with the planet and its moons will continue to provide clues about their origins. Saturn's weather patterns and atmospheric dynamics are also areas of active research. The hexagonal storm at Saturn's North Pole, with its mysterious six-sided structure, challenges our understanding of planetary atmospheres. Similarly, the banded cloud patterns and high-speed winds on Saturn's surface reveal the immense forces at play in the gas giant's atmosphere. These atmospheric phenomena not only shape Saturn's appearance, but also offer a deeper understanding of how gas giants like Jupiter, Saturn, and even exoplanets beyond our solar system behave. The future of Saturn exploration holds great promise. New technologies, including more advanced robotic landers and orbiters, will allow scientists to pry deeper into the planet's mysteries. These missions will likely focus on the potential for life on Saturn's moons, the ongoing evolution of its rings, and the detailed study of its atmosphere and magnetic field. As our technological capabilities improve, we may even envision sending human explorers to the moons of Saturn, continuing humanity's journey outward into the cosmos. In the grand tapestry of the universe, Saturn stands as a reminder of the beauty, complexity, and wonder that awaits those who dare to explore. Its rings, moons, and storms are symbols of the dynamic forces that shape the cosmos, and its study brings us closer to answering some of the most profound questions about the nature of life and the universe itself. Saturn, with all its grandeur, will continue to inspire and challenge us, guiding humanity on its never-ending quest to understand the cosmos and our place within it. As we continue to explore Saturn, we are reminded that each discovery not only deepens our scientific understanding but also expands our perspective on the universe. Saturn, with its vast system of moons, rings, and atmospheric phenomena, is a gateway to some of the most fundamental questions about the cosmos. How do planets and moons form? What are the necessary conditions for life? And, perhaps most intriguingly, are we alone in the universe? One of the most profound aspects of Saturn's exploration is its ability to inspire wonder. The planet's iconic rings, visible even through small telescopes from Earth, have captured the human imagination for centuries. Early astronomers, including Galileo, struggled to understand what they were seeing when they first observed Saturn through rudimentary telescopes. Today, thanks to missions like Cassini, we know that these rings are made of billions of particles of ice and rock, some as small as dust grains, others as large as mountains. The rings themselves are constantly evolving, shaped by gravitational interactions with Saturn's moons and the planet's own magnetic field. These interactions are not just passive phenomena, they represent a delicate balance of forces that govern the behavior of the entire Saturnian system. The so-called shepherd moons, such as Prometheus and Pandora, play a key role in maintaining the structure of the rings. These moons orbit within or near the rings, their gravitational pull creating waves and gaps that add to the rings' dynamic and ever-changing nature. This complex interplay of gravitational forces is a microcosm of the processes that govern planetary formation and the evolution of moons and rings around other planets, both in our solar system and in distant star systems. Saturn's rings are not only a spectacle to behold, but they also offer important insights into the processes that may have shaped their early solar system. Scientists believe that studying the rings can provide clues about the formation of planets and moons, helping us understand how rocky bodies like Earth came to be. Some researchers even suggest that Saturn's rings could be a model for the early stages of moon formation, where particles of ice and rock coalesce to form larger bodies through a process called accretion. In this way, the study of Saturn's rings is not just about understanding the planet itself, but also about uncovering the mechanisms that shape the entire solar system. While Saturn's rings are its most famous feature, the planet's moons are equally compelling. Titan, the largest of Saturn's moons, has become a focal point for scientists seeking to understand the potential for life in extreme environments. Titan's thick atmosphere, composed mostly of nitrogen, is strikingly similar to the early atmosphere of Earth. Its surface, dotted with lakes and rivers of liquid methane and ethane, offers a glimpse of what Earth might have looked like before life emerged. The discovery of organic molecules in Titan's atmosphere has raised the tantalizing possibility that the building blocks of life may exist there, even if life itself has not yet taken hold. Future missions, like NASA's Dragonfly, aim to explore Titan in unprecedented detail. Dragonfly, a rotorcraft lander, will fly across Titan's surface, sampling its atmosphere and surface chemistry, searching for signs of prebiotic chemistry and investigating the moon's potential to support life. This mission is part of a broader effort to explore the outer solar system's icy moons, where liquid water, oceans, and complex chemistry may create environments conducive to life. Dragonfly represents the next chapter in our exploration of Saturn and its moons, continuing the legacy of the Cassini mission and pushing the boundaries of what is possible in planetary exploration. Beyond Titan, the icy moon Enceladus remains one of the most promising candidates in the search for extraterrestrial life. Enceladus, with its subsurface ocean and plumes of water vapor erupting from its south pole, offers a direct window into a potentially habitable environment. These plumes, which contain organic compounds, are a key area of interest for scientists, as they suggest that the Moon's ocean may contain the necessary ingredients for life. The Cassini spacecraft flew through these plumes multiple times, collecting data that has transformed our understanding of Enceladus and its potential habitability. What makes Enceladus particularly exciting is the fact that its subsurface ocean is likely kept warm by hydrothermal vents on the ocean floor. These vents, where water interacts with the Moon's rocky core, could provide the energy needed to sustain life. On Earth, similar hydrothermal vents support thriving ecosystems even in the absence of sunlight, leading scientists to speculate that microbial life could exist in Enceladus's ocean. The discovery of life in such an environment would revolutionize our understanding of biology and the potential for life in the universe, demonstrating that life can thrive in places previously thought to be uninhabitable. Saturn's system, with its diverse collection of moons and dynamic rings, is a testament to the complexity of planetary systems. Each moon offers a unique environment, from the methane lakes of Titan to the icy plumes of Enceladus to the cratered surface of Mimas. These moons create a rich tapestry of worlds that challenge our understanding of planetary science and astrobiology. The study of Saturn's moons not only provides insight into their own unique processes, but also helps scientists develop models for understanding exoplanets and their potential habitability. The exploration of Saturn and its moons is also a reminder of the limitations of our current technology. While missions like Cassini have provided incredible detail about the planet and its system, there is still so much we do not know. The vast distances involved in exploring the outer solar system make it difficult to send frequent missions, and the extreme environments of moons like Titan and Enceladus pose significant challenges for robotic explorers. However, advancements in technology, such as more efficient propulsion systems and more autonomous spacecraft, offer the promise of overcoming these obstacles in the future. Looking ahead, the exploration of Saturn is far from over. There are plans to return to the planet with more sophisticated missions capable of probing deeper into its atmosphere and unlocking the mysteries of its interior. Scientists are also considering missions to land on Enceladus and Titan to drill through the ice and explore the oceans beneath their surfaces. Such missions could provide definitive answers about the potential for life on these moons, offering a glimpse into the broader question of whether life exists beyond Earth. In the broader context of space exploration, Saturn represents one of the great frontiers. It is a reminder that as much as we have learned, there is still so much more to discover. The planet's rings, moons, and atmosphere offer endless opportunities for exploration, pushing the boundaries of science and technology. But beyond the science, Saturn inspires a sense of wonder and curiosity, reminding us of the beauty and complexity of the universe. As we continue to explore this distant giant, we are reminded of the infinite possibilities that await us in the vast expanse of space, and of the profound questions that Saturn and its moons invite us to ask about life, the cosmos, and our place within it. As our exploration of Saturn continues, it's clear that this distant gas giant holds countless secrets waiting to be uncovered. The planet itself, with its iconic rings and vast atmosphere, remains a focal point for understanding not just the dynamics of gas giants, but the broader principles of planetary formation and evolution. Saturn's system, which includes over 80 known moons, offers an unparalleled opportunity to study a diverse array of environments, some of which may be capable of supporting life. One of the most exciting prospects for future exploration lies in deepening our understanding of Saturn's rings. While these rings are Saturn's most famous feature, there are still many unanswered questions about their formation, age, and composition. For years, scientists have debated whether Saturn's rings are a relatively young feature, formed perhaps a few 100 million years ago, or if they date back to the early solar system. Evidence suggests that the rings may be constantly replenished by collisions with comets or moons, which break apart and add material to the system. This dynamic process implies that the rings are not static, but are constantly evolving, shaped by gravitational forces, collisions, and interactions with Saturn's magnetosphere. Newer missions equipped with more advanced instruments could help solve the mystery of Saturn's rings. For instance, studying the rate of dust accumulation within the rings could help scientists determine their age more accurately. Additionally, future spacecraft might analyze the rings' chemical composition in greater detail, providing clues about their origin and the processes that continue to shape them. Understanding Saturn's rings is not just about solving a planetary puzzle. It could also provide insights into the formation of other ring systems around gas giants and even exoplanets. Saturn's atmosphere is another area ripe for exploration. Like Jupiter, Saturn is a gas giant primarily composed of hydrogen and helium. However, the planet's atmosphere is more complex than it first appears. The pale yellow and gold hues we see are the result of ammonia clouds in the upper atmosphere, but beneath these clouds lies a world of turbulent winds, powerful storms, and deep mysteries. One of the most enigmatic features of Saturn's atmosphere is the hexagonal storm at the North Pole, a jet stream that forms a nearly perfect six-sided shape, unlike anything else seen in the solar system. This massive storm, which spans thousands of kilometers, challenges our understanding of atmospheric dynamics and fluid mechanics. Scientists still don't fully understand what causes this hexagonal pattern, although it may be related to differences in wind speeds and the planet's rapid rotation. Future missions could investigate the deep atmosphere of Saturn, probing beneath the cloud layers to study the planet's interior. Saturn's core, like those of other gas giants, is believed to be made of rock and ice, surrounded by layers of metallic hydrogen, a phase of hydrogen that behaves like a metal under extreme pressure. Understanding the structure and composition of Saturn's interior could help scientists model the formation of gas giants, not only in our solar system, but also in distant star systems. With the discovery of thousands of exoplanets, many of which are gas giants, understanding Saturn's inner workings could offer clues about how these planets form and evolve in different environments. The study of Saturn's magnetosphere also holds promise for future discoveries. Saturn's magnetic field, while weaker than Jupiter's, extends far into space, creating a vast magnetosphere that interacts with the solar wind and the planet's rings and moons. Saturn's magnetosphere traps charged particles, creating radiation belts and influencing the behavior of the planet's auroras. These auroras, similar to Earth's northern and southern lights, are caused by the interaction of charged particles with Saturn's magnetic field, producing glowing rings of light at the planet's poles. What makes Saturn's magnetosphere particularly interesting is its interaction with the moons, especially Enceladus. The geysers on Enceladus, which eject water vapor and other materials into space, feed into Saturn's magnetosphere, creating a unique connection between the Moon and the planet's magnetic field. Studying this interaction could provide insights into how magnetospheres influence planetary environments and the potential for habitability. Moreover, Saturn's magnetic field offers a natural laboratory for understanding how magnetic fields might protect or shape exoplanets orbiting distant stars. Saturn's moons continue to captivate scientists, with each one offering a different environment and set of conditions. Titan, the largest of Saturn's moons, stands out as one of the most intriguing bodies in the solar system. With its thick nitrogen atmosphere and surface lakes of liquid methane, Titan is unlike any other moon. It is a world where rivers flow with hydrocarbons instead of water, where organic molecules form in the atmosphere and rain down onto the surface, and where a thick haze obscures the landscape. The upcoming Dragonfly mission will be the first rotorcraft to explore another world. Dragonfly will fly across Titan's surface using its ability to hover and travel to different locations to study the moon's unique chemistry. By sampling the surface and atmosphere, Dragonfly will search for signs of prebiotic chemistry, the processes that could eventually lead to the formation of life. Titan's atmosphere, rich in organic molecules, is believed to resemble that of early Earth, providing a window into how life might have arisen on our own planet. If Dragonfly finds evidence of complex organic chemistry, it could offer crucial insights into the processes that lead to life, not just on Titan but throughout the universe. Enceladus, with its subsurface ocean and icy plumes, remains a prime candidate in the search for extraterrestrial life. The discovery of water-ice geysers on Enceladus by the Cassini spacecraft revolutionized our understanding of this small moon. Cassini flew through these plumes, sampling their composition and detecting organic compounds, salts, and even molecular hydrogen. This finding suggests that hydrothermal activity may be occurring on Enceladus's ocean floor, creating a potential environment for microbial life. Future missions could return to Enceladus to study these plumes in greater detail. By flying through the plumes again, or landing on the surface to collect samples, scientists could search for signs of life, such as microbial organisms or biochemical signatures. The possibility of life existing in the dark, subsurface oceans of Enceladus represents one of the most exciting frontiers in astrobiology. If life can exist in such extreme environments, It would expand our understanding of where and how life can arise in the universe. In addition to Titan and Enceladus, other moons of Saturn, such as Dione and Tethys, offer opportunities for exploration. While they may not have the same potential for habitability as Titan or Enceladus, studying their surfaces, geological activity, and interactions with Saturn's magnetosphere can provide important insights into the history and evolution of the Saturnian system. The study of Saturn, with its rings, moons, and atmosphere, is a journey of discovery that continues to push the limits of human knowledge. Each mission brings us closer to understanding the complex dynamics of this gas giant and its fascinating system of moons. More than just a scientific endeavor, Saturn's exploration is a reminder of the endless curiosity that drives us to explore the cosmos, to seek answers to the deepest questions about our origins, and to expand our horizons beyond the familiar. Saturn, with all its wonders, will continue to inspire future generations of scientists, explorers, and dreamers. Its rings, moons, and storms remind us of the grandeur and complexity of the universe, encouraging us to look beyond our own world and explore the vast, uncharted territories of the cosmos. In this way, Saturn is not just a distant planet, but a symbol of humanity's enduring quest for knowledge and understanding. As we push further into the exploration of Saturn and its captivating system, the lessons we learn extend far beyond just understanding this gas giant. Each mission, each discovery expands our comprehension of planetary science, the potential for life, and the mechanics that govern not only our solar system but also the many others scattered across the galaxy. The story of Saturn, in many ways, is the story of the universe, diverse, dynamic, and full of unexpected wonders. One of the key scientific questions that continues to captivate researchers is the origin and age of Saturn's rings. These vast, shimmering structures have become a symbol of cosmic beauty, but their origins remain a mystery. Some models suggest that the rings formed relatively recently, within the last 100 million years, possibly from the remnants of a destroyed moon or a comet that wandered too close to Saturn and was torn apart by the planet's powerful gravity. Other hypotheses propose that the rings could be ancient, dating back to the early solar system. This debate about the age and origin of Saturn's rings touches on fundamental questions about how planetary systems evolve over time and the processes that shape them. The thinness of Saturn's rings, despite their immense breadth, is also a puzzle. They are incredibly flat, often only a few meters thick, despite being hundreds of thousands of kilometers in diameter. This suggests that the particles within the rings must be interacting in complex ways, governed by Saturn's gravitational field as well as the influence of its moons. Observations from the Cassini mission have revealed intricate structures within the rings, such as waves and ripples caused by the gravitational interactions with the moons, known as shepherding moons, and help maintain the rings' delicate balance. Beyond their visual beauty, Saturn's rings serve as a laboratory for understanding broader cosmic phenomena. The way the particles in the rings interact provides a glimpse into the process of accretion, the same process that helped form planets and moons in the early solar system. By studying these dynamics, scientists can learn more about how materials clump together under the influence of gravity to form larger bodies, a process that could be occurring around young stars throughout the galaxy, leading to the formation of new planetary systems. Saturn's magnetosphere, a vast region dominated by the planet's magnetic field, is another area of ongoing exploration. The planet's magnetic field, generated by the movement of conductive materials within its core, extends millions of kilometers into space, creating a protective bubble that deflects the solar wind. This magnetosphere interacts with the planet's rings, moons, and the particles within its own atmosphere, influencing everything from the planet's stunning auroras to the behavior of its moons. One of the most fascinating aspects of Saturn's magnetosphere is how it interacts with the icy moon Enceladus. The geysers on Enceladus eject water vapor, ice, and organic materials into space, feeding into Saturn's magnetosphere and creating a unique relationship between the moon and the planet. These interactions produce complex electrical currents that not only affect Saturn's magnetic field but also help create the planet's powerful auroras. This connection between Enceladus and Saturn's magnetosphere has opened up new avenues of research into how moons can influence the planets they orbit and vice versa. Saturn's complex weather patterns, including its infamous storms, also provide key insights into planetary atmospheres. While Jupiter's Great Red Spot is perhaps the most famous storm in the solar system, Saturn has its own notable atmospheric features, including the hexagonal jet stream at the planet's north pole. This six-sided storm has puzzled scientists for decades, as its shape defies conventional atmospheric models, measuring roughly 30,000 kilometers across. The hexagon rotates at a rate similar to Saturn's rotational period, yet the mechanism behind its perfect geometry remains unclear. Some scientists believe it is caused by a standing wave pattern deep in Saturn's atmosphere, while others suggest that it could be related to the planet's rapid rotation and the unique properties of its atmospheric layers. In addition to the hexagonal storm, Saturn experiences periodic superstorms, known as Great White Spots, which occur roughly once every 30 years. These massive storms, large enough to be visible from Earth, can span thousands of kilometers and last for months. They serve as natural laboratories for understanding the dynamics of planetary weather systems, offering parallels to similar storm systems on other gas giants, including Jupiter and even exoplanets orbiting distant stars. Studying these storms can help scientists understand the physics of large-scale weather patterns and how they evolve over time in different planetary environments. Of course, Saturn's moons remain one of the most promising areas of study, particularly when it comes to the search for life beyond Earth. Titan, with its thick atmosphere and lakes of liquid methane, has long been considered one of the most Earth-like bodies in the solar system, albeit under very different conditions. The discovery of complex organic molecules in Titan's atmosphere, combined with its dense haze and hydrocarbon lakes, has made it a prime candidate for exploring how life might arise in environments drastically different from our own. The upcoming Dragonfly mission, which will send a drone-like rotorcraft to explore Titan's surface, represents a major leap forward in the study of this fascinating moon. Dragonfly will be able to sample Titan's atmosphere, analyze the composition of its surface, and search for signs of prebiotic chemistry. Titan's atmosphere may offer clues about how life began on Earth, while its methane lakes could reveal new insights into chemistry that occurs in environments much colder than anything we experience on our planet. Enceladus, with its subsurface ocean and water ice geysers, remains another primary target in the search for extraterrestrial life. The discovery of organic molecules and salts in the plumes ejected from Enceladus's southern pole suggests that hydrothermal activity is occurring deep within the moon, potentially providing the energy needed to sustain microbial life. Future missions to Enceladus could involve landers or subsurface probes that directly sample the moon's icy crust or ocean, searching for biomarkers or other signs of life. As we continue to explore Saturn and its moons, it is clear that this distant world holds keys to understanding not only our own solar system but the broader processes that govern planetary formation, atmospheric dynamics, and the potential for life in the universe. Each mission to Saturn builds on the discoveries of the past, offering new insights and posing new questions about the nature of our cosmic neighborhood. Saturn stands as a reminder of the vastness and complexity of the universe. Its rings, moons, and atmosphere challenge our understanding of planetary systems and invite us to explore the unknown. As future missions venture back to this gas giant and its intriguing moons, we are likely to discover even more surprises, new clues that will deepen our knowledge of the cosmos and our place within it. With all its majesty and mystery, will continue to inspire awe, curiosity, and scientific exploration for generations to come. The future exploration of Saturn promises to uncover even more astonishing insights about this giant of the solar system, extending our understanding not only of the planet itself but also of the broader mechanisms that shape planetary systems. Each discovery at Saturn reveals new layers of complexity, further proving that the universe is far more intricate and diverse than we ever imagined. As our technology advances, we stand on the brink of learning more than ever about this gas giant, its spectacular rings, and its enigmatic moons. One of the next frontiers in Saturn's exploration lies in understanding the long-term evolution of its ring system. While the Cassini mission provided unprecedented detail about the structure and composition of Saturn's rings, there is still much we don't know about how they formed and what their ultimate fate might be. Are the rings a temporary phenomenon, destined to fade over time as material drifts away or falls into the planet's atmosphere? Or are they continually replenished through collisions with moons or other celestial bodies? Some scientists hypothesize that Saturn's rings may be eroding, and over the course of millions of years, they could disappear altogether. Future missions could focus on these questions, providing a clearer timeline for the life cycle of planetary ring systems. To fully understand Saturn's rings, future spacecraft might deploy more sophisticated instruments designed to measure the precise composition of the ring particles. Such missions could also capture high-resolution images of the intricate structures within the rings, including the many gaps, waves, and braided patterns that result from gravitational interactions with Saturn's moons. By mapping these features over time, scientists could track how the rings evolve on short timescales, providing insights into the dynamic processes at work within this complex system. Another exciting area for future exploration is the deeper layers of Saturn's atmosphere. Much like the other gas giants, Saturn's visible cloud tops are just the surface of an immensely deep and mysterious atmosphere where pressures and temperatures increase dramatically with depth. Beneath the familiar ammonia clouds that give Saturn its characteristic yellowish hue lies a world of swirling hydrogen and helium, transitioning into exotic states of matter like metallic hydrogen, which exists under the immense pressures found deeper within the planet. Understanding the transitions within Saturn's atmosphere is crucial to answering questions about its internal structure, including whether the planet has a solid core. Missions designed to probe Saturn's deeper atmosphere could give us vital information about the distribution of elements within the planet and the processes that drive its massive, high-speed winds and long-lasting storms. These atmospheric probes could provide data that help scientists model gas giants throughout the galaxy, shedding light on how planets of such immense size form and evolve. The giant hexagonal storm at Saturn's North Pole remains one of the most perplexing features of the planet's atmosphere. This massive, six-sided jet string, which has been observed for decades, doesn't conform to the usual patterns we see in planetary atmospheres. The exact mechanisms driving this storm are still debated, but it is believed to be related to the planet's rotation and the unique dynamics of its atmosphere. Studying this storm in greater detail, perhaps through long-duration atmospheric probes or even aerial vehicles that could float in Saturn's upper atmosphere, might finally provide answers to this puzzle and help explain why similar phenomena aren't seen on other planets in our solar system, while Saturn itself remains a focus. The planet's diverse moons offer equally tantalizing prospects for future missions. Titan, with its thick atmosphere, lakes of liquid methane, and complex organic chemistry, continues to be one of the most promising worlds in the search for life. The upcoming Dragonfly mission will give us an unprecedented look at this moon as it flies from location to location, taking samples of Titan's surface and atmosphere and studying its potential for prebiotic chemistry. Dragonfly will focus on areas where Titan's atmosphere interacts with its surface, particularly in regions where liquid methane and ethane flow, creating features that resemble Earth's lakes and rivers. Titan's thick atmosphere and cold temperatures create a unique environment for organic molecules to form and evolve, and Dragonfly's suite of instruments is designed to analyze these molecules in detail. By understanding how organic molecules behave on Titan, we can gain insight into how life might arise in environments that are vastly different from Earth. The potential for life on Titan, while speculative, is deeply exciting. Some scientists suggest that Titan's surface might host life forms that use methane in a way similar to how Earth-based life uses water. Others believe that life might exist beneath Titan's icy crust, where water could be present in a subsurface ocean, similar to the conditions believed to exist on Europa and Enceladus. These possibilities challenge our Earth-centric view of life and push the boundaries of what we consider habitable. Enceladus remains another prime candidate in the search for life beyond Earth, particularly because of its water-ice geysers that erupt from cracks in its surface, suggesting the presence of a subsurface ocean. The discovery of organic molecules in these geysers by the Cassini spacecraft has only heightened interest in this small moon. Future missions could send landers to Enceladus's surface or submersible probes capable of penetrating the ice crust and exploring the moon's ocean directly. The plumes of Enceladus represent one of the easiest ways to sample a potential extraterrestrial ocean without having to drill through thick ice. By flying through these plumes and analyzing their contents, scientists hope to find more definitive evidence of the conditions necessary for life. In the long term, a mission designed to land near the plume sources and take direct samples could provide unprecedented information about the moon's chemistry, geology, and potential biology. Even the moons that seem less likely to harbor life, such as Iapetus with its dramatic surface dichotomy, or Mimas with its massive impact crater, hold clues about the history of the Saturnian system. These moons are natural archives, preserving the record of billions of years of cosmic history. Studying their surfaces, geological activity, and interactions with Saturn's magnetosphere can help scientists understand how moons evolve in the shadow of a giant planet, and what processes shape their landscapes over time. The exploration of Saturn is not just about uncovering facts about a distant planet, it is also a journey that pushes the limits of human understanding and imagination. Saturn's system, with its rings and moons, represents a microcosm of the processes that govern the universe. The gravitational forces, magnetic fields, atmospheric dynamics, and chemical interactions occurring at Saturn can all be scaled up to help explain the behavior of exoplanets, distant star systems, and even galaxies. As humanity looks to the future, Saturn stands as a symbol of our capacity to explore, discover, and dream. Its beauty, complexity, and mystery inspire us to continue probing the unknown, to ask questions that stretch our understanding, and to seek answers in the farthest reaches of space. With each new mission to Saturn, we take another step closer to answering some of the most profound questions about the nature of the universe and our place within it. The journey to Saturn has only just begun. As future generations of explorers and scientists look to the stars, Saturn will remain a key destination, offering endless opportunities for discovery and wonder. The mysteries of this gas giant and its moons will continue to unfold, drawing us deeper into the cosmic story that began with our first glimpses through a telescope, and will continue as long as humanity reaches for the stars. The journey to explore Saturn and its system is a testament to human curiosity and resilience. With each new mission, we are reminded of the vastness of the universe and the intricacies that lie hidden within our own solar system. Saturn, as majestic and awe-inspiring as it is, remains a focal point for not just planetary science, but for fundamental questions about the nature of life, the formation of planetary systems, and the forces that govern the cosmos. One of the exciting developments in Saturn exploration is the increasing collaboration between international space agencies. NASA's Cassini mission, which brought unprecedented insights into Saturn's rings, moons, and atmosphere, was a joint effort with the European Space Agency ESA and the Italian Space Agency EASA. This international cooperation is becoming more prevalent in space exploration, as the challenges of sending missions to the outer solar system require a combination of resources, expertise, and vision from across the globe. The future of Saturn exploration will likely see even more collaborations, bringing together the scientific communities of multiple countries to answer the big questions. How do gas giants like Saturn evolve over time? What role do their rings and moons play in the formation of planetary systems? And perhaps most compellingly, could the conditions on Saturn's moons harbor life? One of the next significant steps in Saturn exploration could be the development of more advanced landers and probes capable of exploring the surfaces and subsurface oceans of moons like Titan and Enceladus. While Cassini provided a wealth of data from orbit and flybys, landing on these moons, or even sending a submarine-like vehicle into Enceladus's ocean, could give us direct access to the environments most likely to harbor life. The technologies required for such missions are advancing rapidly. Robotic explorers are becoming more autonomous, able to navigate complex terrain and make decisions on their own. Instruments are being miniaturized and becoming more sensitive, allowing us to detect even the faintest chemical signatures of life. One proposed mission involves sending an ice-penetrating probe to Enceladus, capable of boring through the icy crust and diving into the ocean below. This type of mission, while ambitious, could revolutionize our understanding of ocean worlds and their potential for life. Similarly, the Dragonfly mission to Titan, set to launch in the mid-2020s, will be a bold step in exploring the surface of a moon that, in many ways, resembles early Earth. Dragonfly will fly from site to site, using its rotorcraft to take samples and analyze the chemical composition of Titan's surface and atmosphere. It will search for signs of prebiotic chemistry, offering crucial insights into how life might form in environments far different from our own. This mission is an exciting blend of innovation and exploration, taking us closer than ever before to understanding Titan's potential as a cradle for life. Enceladus remains another critical target in the search for life. Its water ice plumes offer a rare opportunity to sample material from a subsurface ocean without having to drill through kilometers of ice. Cassini's flybys through these plumes detected organic molecules, raising the tantalizing possibility that life could exist in the dark, salty waters beneath Enceladus's surface. Future missions might involve landers designed to study the ice and the material ejected from these plumes in greater detail, or even send small submersibles into the ocean itself. The implications of finding life, or even the building blocks of life, on Enceladus or Titan would be profound. It would suggest that life is not unique to Earth, but rather a natural consequence of the right conditions coming together. It would open the door to the idea that life could exist throughout the galaxy, in environments that we might currently consider inhospitable. Discovering life on one of Saturn's moons would fundamentally change our understanding of biology, planetary science, and our place in the universe. But beyond the scientific allure of discovering life, the study of Saturn and its moons also brings us closer to understanding the processes that shape planetary systems across the universe. Gas giants like Saturn play a crucial role in the formation of planetary systems. Their massive gravitational fields influence the orbits of smaller planets and bodies, and their rings and moons offer a glimpse into how these systems evolve over time. By studying Saturn, we learn not just about our solar system, but about the countless other systems scattered across the galaxy. Saturn's own moon system is a miniature solar system in its own right, with over 80 moons orbiting the planet. Each of these moons has its own unique story. Some, like Titan, have dense atmospheres and complex surface chemistry. Others, like Mimas and Dione, are heavily cratered and may represent more ancient records of Saturn's early history. Studying these moons gives scientists a better understanding of the diversity of planetary bodies and the various paths they can take during their formation and evolution. The moons also provide a natural laboratory for studying how moons interact with their parent planet. Gravitational interactions between Saturn and its moons can cause tidal heating, as seen on Enceladus, where the moon's interior is warmed by the stretching and squeezing caused by Saturn's gravity. This heating could be responsible for keeping the ocean beneath Enceladus's icy crust liquid, and similar processes might be at work on other icy moons in the outer solar system. The study of Saturn's magnetosphere also offers valuable insights into how planetary magnetic fields interact with the solar wind and the particles ejected from the planet's atmosphere and rings. Saturn's magnetosphere is one of the largest and most powerful in the solar system, and its interaction with the solar wind creates complex patterns of radiation and auroras. These processes are not only interesting in their own right, but also provide important clues about how magnetic fields might protect planets or moons from the harsh conditions of space. Future missions could take a closer look at Saturn's magnetosphere, using more advanced instruments to map its structure and study how it interacts with the planet's atmosphere, rings, and moons. This could provide a clearer understanding of how planetary magnetic fields influence the evolution of planets and their potential for habitability. As we look ahead, the future of Saturn exploration is filled with possibilities. There is so much more to learn, from the chemical composition of its moons to the dynamics of its rings and the mysteries of its atmosphere. And yet, Saturn is just one part of a much larger puzzle. Each discovery we make there adds to our understanding of the solar system as a whole and the processes that shape the universe. Perhaps the most exciting prospect of all is that the exploration of Saturn may finally answer the question that has fascinated humanity for millennia. Are we alone in the universe? The search for life on Enceladus, Titan, and other moons in the outer solar system could yield the first evidence that life exists beyond Earth. And even if we don't find life, the discoveries we make about these distant worlds will reshape our understanding of what it means to be alive and what conditions might foster life in other parts of the galaxy. As we continue to send probes and missions to Saturn, we are embarking on a journey that will redefine our place in the cosmos. Saturn's rings, moons, and storms will continue to inspire awe and curiosity, driving humanity to explore further, to push the boundaries of what we know, and to seek answers to the deepest questions about the universe and our place within it. The journey of exploration to Saturn and beyond is emblematic of humanity's relentless pursuit of knowledge and the deep desire to uncover the mysteries of the universe. Saturn, with its awe-inspiring rings, enigmatic moons, and powerful storms, offers a profound glimpse into the workings of not only our solar system but the cosmic mechanics that govern planetary systems throughout the galaxy. As our exploration advances, the question of Saturn's long-term evolution becomes increasingly important. One intriguing aspect scientists are eager to understand is how Saturn's massive atmosphere changes over time. Saturn's atmosphere, composed primarily of hydrogen and helium, is constantly buffeted by powerful winds and intense storms. The largest of these storms, the periodic Great White Spot, occurs roughly once every 30 Earth years and is massive enough to encircle the entire planet. These superstorms, which are much larger than any weather event seen on Earth, provide a unique opportunity to study planetary atmospheres in extreme conditions. What drives these massive storms, and how do they shape Saturn's atmospheric evolution? By studying Saturn's atmosphere over long periods, scientists hope to uncover the mechanisms behind these periodic events. Understanding the behavior of Saturn's atmosphere is not only important for its own sake, but also provides clues about the atmospheres of other gas giants in our solar system, like Jupiter, Uranus, and Neptune, as well as exoplanets that orbit distant stars. In addition to atmospheric research, the study of Saturn's moons remains a central focus of planetary exploration. As we delve deeper into these mysterious worlds, it becomes clear that Saturn's moon system represents an extraordinary laboratory for understanding how moons form, evolve, and interact with their parent planet. One of the most fascinating moons, Titan, stands out as a world that may hold the key to answering one of the most profound questions in science. How does life begin? Titan, with its thick atmosphere and surface lakes of liquid methane, is unlike any other moon in the solar system. Its dense, nitrogen-rich atmosphere is similar to what scientists believe Earth's atmosphere might have been like before life emerged. Methane, which exists as a liquid on Titan due to its frigid temperatures, forms lakes, rivers, and even rain, creating an active weather system that mirrors the water cycle on Earth. These surface processes, combined with Titan's rich organic chemistry, make it a prime candidate for studying the building blocks of life. NASA's Dragonfly mission, set to explore Titan in the 2030s, will be the first mission to explore multiple locations on the moon's surface. Using a rotorcraft, Dragonfly will hop from one site to another, taking samples and conducting experiments to determine the chemical composition of Titan's surface and atmosphere. It will search for prebiotic chemistry, the chemical processes that could lead to the formation of life. By analyzing these processes, Dragonfly may help scientists understand how life could arise on other worlds with environments vastly different from Earth's. What makes Titan particularly exciting is the possibility of finding life forms that rely on methane rather than water as a solvent. While this concept is still speculative, it challenges the traditional assumptions about where life might exist. If life, or even the precursors to life, can form in the harsh, cold environment of Titan, it would suggest that life is far more adaptable and resilient than previously thought. Titan could reveal that the ingredients for life are not unique to Earth, expanding the scope of astrobiology and redefining the search for life beyond our planet. Enceladus, another of Saturn's moons, continues to captivate scientists with its potential habitability. The discovery of water ice geysers erupting from the moon's south pole by the Cassini spacecraft revolutionized our understanding of this small icy world. These geysers, which are believed to originate from a subsurface ocean beneath Enceladus's icy crust, offer a direct window into the moon's interior. The presence of organic molecules and molecular hydrogen in the plumes suggests that hydrothermal activity is occurring on the ocean floor, creating conditions that could support life. On Earth, similar hydrothermal vents in the deep ocean provide the energy needed to sustain rich ecosystems even in the absence of sunlight. Could similar ecosystems exist beneath Enceladus's icy surface? Future missions could be designed to fly through these plumes again, collecting more detailed samples, or even land on the moon's surface to search for direct evidence of microbial life. The exploration of Enceladus presents one of the most exciting opportunities in the search for life beyond Earth. It is one of the few places in the solar system where we know liquid water exists in significant quantities, and its subsurface ocean is protected from the harsh radiation environment of space by the moon's thick ice shell. The combination of water, organic molecules, and a possible energy source makes Enceladus a prime candidate for habitability. As scientists continue to develop new technologies, missions to Enceladus could become even more ambitious. Some proposals involve sending a lander to the moon's surface, equipped with drills or melting probes that could penetrate the ice and explore the ocean beneath. Other concepts envision submersible robots capable of exploring the depths of Enceladus's ocean, searching for signs of life in the dark, cold waters. These missions, while technically challenging, could provide the first direct evidence of extraterrestrial life and transform our understanding of biology. While Titan and Enceladus hold the most promise in terms of habitability, Saturn's other moons also offer valuable insights into planetary science. Moons like Mimas, Dione, and Rhea are heavily cratered and geologically less active than Titan or Enceladus. But they preserve records of Saturn's early history. Studying their surfaces and interiors can help scientists piece together the timeline of the Saturnian system, providing clues about how the moons and rings formed and evolved over billions of years. Saturn's rings, meanwhile, continue to intrigue scientists with their dynamic nature. The delicate balance of gravitational forces between the planet and its moons shapes the structure of the rings, creating gaps, waves, and other intricate features. Observations from the Cassini mission revealed that the rings are far younger than Saturn itself, raising questions about their origin. Some scientists propose that the rings may be the remnants of a shattered moon or a captured comet, while others suggest they could be the result of material left over from Saturn's formation. Understanding the lifespan of Saturn's rings is another key question for future exploration. Are the rings a temporary feature slowly eroding over time, or could they be replenished by ongoing collisions and gravitational interactions? Missions designed to study the rings in greater detail could help answer these questions, providing a clearer picture of how ring systems evolve and how long they might last. In addition to revealing the history of Saturn's system, studying the rings could also offer insights into how planetary systems form and evolve across the galaxy. Rings are thought to be a common feature of gas giants and other star systems, and understanding the processes that govern Saturn's rings could help scientists model the formation of similar systems around distant exoplanets. The exploration of Saturn and its moons is about much more than just understanding one planet. It is about answering some of the most profound questions in science. How do planets and moons form? What conditions are necessary for life? And what can these distant worlds teach us about the universe as a whole? As future missions set their sights on Saturn, we are likely to uncover even more surprises. With each new discovery, we deepen our understanding of the cosmos and our place within it. Saturn, with its stunning rings and diverse moons, will continue to inspire generations of scientists, explorers, and dreamers, reminding us that the universe is vast, full of wonder and waiting to be explored. The future of Saturn exploration is poised to reveal answers to some of the most pressing and tantalizing questions in planetary science, particularly concerning the formation and evolution of planetary systems, the nature of gas giants, and the potential for life in environments that are dramatically different from our own. With Saturn's diverse system of moons and its iconic rings, this gas giant offers a treasure trove of scientific opportunities, each discovery deepening our understanding of the cosmos and challenging our preconceptions. One of the key areas of interest in future Saturn missions will be the continued study of its fascinating moons. Titan and Enceladus, both of which are already targets for upcoming exploration, will play central roles in our ongoing search for life beyond Earth. Titan's surface, with its lakes of methane and ethane, provides a rare opportunity to study a prebiotic world, one that might hold clues to how life could begin in environments drastically different from those on Earth. The Dragonfly mission, scheduled for launch in 2027, will allow us to explore Titan's surface in unprecedented detail, hopping between diverse locations to investigate the moon's potential for complex organic chemistry and prebiotic processes. As Dragonfly soars through Titan's thick atmosphere, it will examine the interaction between the moon's surface and its atmosphere, giving us a better understanding of the complex methane cycle that shapes Titan's weather and geology. By studying these processes in detail, Dragonfly may also provide insights into the chemical pathways that lead to the formation of life. This mission is a groundbreaking step forward in astrobiology and planetary science, offering the possibility of finding the chemical precursors of life on a world that, despite its extreme cold and alien conditions, might echo the early Earth. Enceladus remains a prime candidate in the search for extraterrestrial life. The discovery of water ice geysers erupting from its south pole by the Cassini mission opened a window into a hidden, subsurface ocean that might be teeming with microbial life. The detection of organic molecules and molecular hydrogen in these plumes strongly suggests that hydrothermal activity is occurring on Enceladus's ocean floor, creating a potentially habitable environment similar to deep-sea hydrothermal vents on Earth. Future missions to Enceladus could focus on more detailed analysis of the plumes and the ocean below. Some proposals include landers designed to touch down near the geysers, collecting samples of ice and vapor for in-depth analysis. Others envision sending submersible probes that could melt through Enceladus's ice shell and explore the ocean itself, searching for signs of life in the dark, icy waters. These missions would be incredibly ambitious and technically challenging, but the potential payoff is enormous. Finding life in Enceladus's ocean would not only confirm that life can exist in extreme environments, but also revolutionize our understanding of biology and the potential for life across the universe. Beyond Titan and Enceladus, Saturn's other moons, such as Rhea, Iapetus, and Dione, offer valuable insights into the history and evolution of the Saturnian system. Many of these moons are heavily cratered, preserving records of the early solar system and providing clues about the processes that shaped the moons and Saturn's rings. Some moons, like Iapetus, present strange and unexplained features. Iapetus has a striking two-tone surface with one hemisphere much darker than the other and a massive equatorial ridge that stretches around much of the moon. These unusual characteristics raise questions about the moon's history, its formation, and the forces that have acted upon it over billions of years. Understanding the geologic and dynamic history of Saturn's moons will provide important context for the formation of moons and other planetary systems. The study of these moons can help scientists build more accurate models of moon formation and evolution, offering insights into how moons like ours might have formed around other planets across the galaxy. Saturn's rings, of course, remain one of the most visually stunning and scientifically intriguing features in the solar system. The Cassini mission provided unprecedented detail about the ring's structure, composition, and dynamics, but many questions remain. Are the rings a relatively recent phenomenon, formed perhaps by the destruction of a moon or comet, or have they been a feature of Saturn for billions of years? Are they slowly eroding, or do they represent a stable system that could persist for a long time? The composition of the rings, particularly the balance between icy and rocky material, holds clues to their origin and long-term evolution. Future missions designed to study Saturn's rings could focus on measuring their precise composition and mapping how they interact with Saturn's moons and magnetic field. The gravitational interactions between Saturn's moons and the rings create complex patterns of waves, gaps, and divisions within the rings, which could reveal important information about the formation and behavior of ring systems around other gas giants. By studying Saturn's rings, scientists can learn more about the dynamics of ring systems and how they evolve over time, offering a model for understanding similar systems around exoplanets. Saturn's atmosphere is another area ripe for further exploration. The periodic superstorms, known as Great White Spots, as well as the mysterious hexagonal storm at the North Pole, present puzzles that scientists are eager to solve. Saturn's atmosphere is a complex system of high-speed winds, chemical reactions, and long-lasting storms, driven by the planet's rapid rotation and the intense internal heat generated within its core. Understanding these atmospheric dynamics is key to unraveling the behavior of gas giants, not only in our solar system but across the galaxy. Missions designed to probe Saturn's atmosphere could give us valuable information about the planet's deep interior, where pressures and temperatures rise to extreme levels. Studying the transition from the gaseous outer layers to the metallic hydrogen deep within Saturn's atmosphere will provide clues about the planet's internal structure, including whether it has a solid core. This information could be applied to exoplanets, especially gas giants that orbit distant stars, helping scientists understand how such planets form and evolve over time. The exploration of Saturn's magnetosphere also holds promise for future missions. Saturn's magnetic field, generated by the movement of conductive material deep within the planet, creates a massive magnetosphere that interacts with the solar wind, the planet's rings, and its moons. These interactions create auroras at Saturn's poles and influence the behavior of particles within the planet's atmosphere. Understanding how Saturn's magnetosphere interacts with its moons, particularly with Enceladus's geysers, will help scientists understand the broader role of magnetic fields in shaping planetary systems. As we continue to explore Saturn, we are reminded that the gas giant is not just a solitary world. It is a system unto itself, with each moon, ring, and storm contributing to a dynamic and interconnected environment. The study of Saturn offers a glimpse into the processes that shape not only our solar system but also planetary systems across the galaxy. The discoveries we make at Saturn have far-reaching implications, from understanding the origins of planets and moons to identifying the conditions necessary for life. The future of Saturn exploration is bright, filled with potential discoveries that will reshape our understanding of the universe. Whether through the continued search for life on Titan and Enceladus, the study of Saturn's rings and moons, or the deep exploration of the planet's atmosphere and magnetosphere, Saturn remains a gateway to the cosmos, a place where science, exploration, and imagination converge. As we send new missions to this distant world, we are not just exploring Saturn, we are expanding the horizons of human knowledge and preparing for the next great chapter in our journey through the stars. The unfolding story of Saturn is one that reflects the core of human ambition, to push beyond the boundaries of what we know, to explore the unknown, and to seek answers to the deepest questions about our universe. With each new mission to this majestic gas giant, we expand not only our scientific knowledge, but also our sense of wonder and possibility. Saturn, with its rings and moons, its powerful magnetic fields, and its complex atmosphere, serves as a reminder of how much more there is to learn about our solar system, and by extension, the cosmos. As we look to the future of Saturn exploration, the potential for discovery feels limitless. The moons of Saturn, particularly Titan and Enceladus, are at the heart of our quest to understand the origins of life. Titan's thick atmosphere and liquid methane lakes create an environment that might offer parallels to the early Earth, while Enceladus, with its subsurface ocean and organic-rich geysers, represents one of the most promising candidates for life beyond our planet. The Dragonfly mission to Titan is expected to revolutionize our understanding of this fascinating moon. As it flies across the surface, hopping from one scientifically interesting site to another, Dragonfly will analyze the chemical makeup of Titan's surface and atmosphere in ways that were previously unimaginable. The presence of complex organic molecules in Titan's atmosphere suggests that prebiotic chemistry might already be underway, and Dragonfly's instruments are designed to search for evidence of these chemical processes. The mission will also help answer questions about the methane cycle on Titan, how methane moves through the atmosphere and what drives the formation of the lakes, rivers, and rain that make Titan so unique. This mission is more than just an exploration of one moon. It is a step toward understanding the conditions under which life might emerge on worlds far different from our own. If we find even the faintest signs of prebiotic chemistry on Titan, it could fundamentally reshape our understanding of how life begins, not only on Earth-like worlds, but in the most unexpected environments. At the same time, the ongoing exploration of Enceladus promises to yield even more exciting discoveries. The detection of organic molecules in the plumes erupting from Enceladus's surface has fueled speculation about the potential for life in its hidden ocean. The fact that these plumes contain hydrogen, a key energy source for microbial life on Earth, suggests that conditions in Enceladus's ocean might be similar to those found near deep-sea hydrothermal vents, where life thrives in complete darkness. Future missions to Enceladus could be designed to dive deeper into these plumes, collecting samples of the water vapor and ice particles to search for more complex organic molecules or even microbial life. Some proposed missions envision sending a lander or even a probe that could penetrate the ice and explore the ocean directly. Such a mission, though technically challenging, would represent a giant leap forward in astrobiology, offering the first real opportunity to search for life in an extraterrestrial ocean. But Saturn's system is about much more than just a search for life. The planet itself, with its immense size, fast winds, and dramatic weather patterns, offers a window into the behavior of gas giants throughout the universe. Saturn's atmosphere is home to some of the most extreme weather in the solar system, including storms that last for years and winds that can reach speeds of over 1,800 kilometers per hour. These phenomena are driven by complex interactions between the planet's rotation, its internal heat, and the chemical processes occurring within its thick clouds of hydrogen and helium. One of the most enigmatic features of Saturn's atmosphere is the massive hexagonal storm at its north pole. This six-sided jet stream has fascinated scientists since it was first observed by the Voyager spacecraft in the 1980s, and its exact cause remains a mystery. Some researchers believe it may be caused by a combination of fast winds and the planet's unique rotation, but no other storm like it has ever been observed on any other planet. Studying the storm could lead to new insights into atmospheric dynamics, not just on Saturn, but on other gas giants and even exoplanets beyond our solar system. The periodic Great White Spot storms, which erupt in Saturn's northern hemisphere every 30 Earth years, are another area of interest. These massive storms, which can cover the entire planet, are thought to be driven by changes in Saturn's deep atmosphere. By studying the formation and behavior of these storms, scientists hope to gain a better understanding of the complex forces that drive weather on gas giants. Saturn's rings, too, remain a source of fascination. Though we have learned much about them thanks to the Cassini mission, many questions about their origin and future remain. The rings are made of billions of particles of ice and rock, ranging in size from tiny grains to massive boulders, all orbiting Saturn in a delicate gravitational dance. The fact that the rings are relatively young, possibly only a few 100 million years old, raises questions about how they formed and how long they will last. Some scientists believe the rings could be the remnants of a moon that was destroyed by Saturn's gravity, while others suggest they may have formed from material left over from the planet's formation. Understanding the processes that shape Saturn's rings could help scientists model the behavior of ring systems around other planets, including the rings of distant exoplanets. As we continue to study Saturn's rings, we may also learn more about the forces that govern planetary systems and the evolution of gas giants across the universe. Saturn's magnetosphere, the bubble of charged particles and magnetic fields that surrounds the planet, is another area of active research. Saturn's magnetic field is one of the strongest in the solar system, and it plays a crucial role in shaping the environment around the planet. The interaction between Saturn's magnetosphere and its moons, particularly Enceladus, has revealed new insights into how magnetic fields influence planetary systems. The geysers on Enceladus, for example, eject water vapor and particles that become trapped in Saturn's magnetic field, creating a complex web of interactions that shape both the moon and the planet. Future missions could explore Saturn's magnetosphere in greater detail, using more advanced instruments to map its structure and study how it interacts with the solar wind and the planet's moons. This research could provide new insights into how magnetic fields protect planets from harmful cosmic radiation, a key factor in the search for habitable worlds beyond our solar system. In the coming decades, as new missions are sent to Saturn and its moons, we are likely to make discoveries that will change the way we see the universe. Whether it's the detection of life on Enceladus or Titan, a deeper understanding of Saturn's atmospheric and magnetic dynamics, or new revelations about the planet's rings, each discovery will add to our growing knowledge of the cosmos. Saturn's exploration is not just about answering scientific questions, it's about pushing the boundaries of what's possible. Each mission to this distant world represents a triumph of human ingenuity, collaboration, and curiosity. As we continue to explore Saturn and beyond, we are reminded that the universe is vast, full of mystery and waiting to be explored. The discoveries we make on Saturn and its moons will not only reshape our understanding of the solar system, but also inspire future generations of explorers to continue reaching for the stars. In conclusion, the exploration of Saturn and its extraordinary system of rings and moons stands as one of humanity's most profound scientific endeavors. Each new mission deepens our understanding of the complex forces that shape not only our solar system but planetary systems throughout the cosmos. From the mysteries of Titan's thick atmosphere and methane lakes to the tantalizing potential of life beneath the icy crust of Enceladus. Saturn's moons offer unparalleled opportunities for discovery and insight into the origins of life itself. Saturn's iconic rings, vast magnetic field, and dynamic weather systems invite us to explore the fundamental processes that govern gas giants, while its unique hexagonal storm and the periodic great white spots reveal the intricate nature of planetary atmospheres. The continuing study of Saturn, enriched by missions like Cassini and the upcoming Dragonfly, propels us into a future where we may not only uncover the origins of our own solar system, but also learn how these processes might unfold on worlds far beyond our own. As we look toward the next chapters of exploration, Saturn serves as a beacon of wonder, reminding us that the universe is filled with mysteries waiting to be solved. The discoveries we make will not only expand our scientific knowledge, but also inspire future generations to dream, explore, and reach for the stars. In our quest to understand Saturn, we are reminded of the boundless curiosity that drives us to push beyond our horizons, to seek the unknown and to embrace the infinite possibilities of the cosmos.